IA equal to 30 ampere. The next problem. Determine the current in the element of the three-phase data connected heater, which has an impedance of the 41.5 ohm per phase when it is connected to a 415 volt 3-watt supply if the fuse in the phase C has a blown. So in this case, this is the connection, data connection, 41.5 ohm, data connection, supply voltage V equal to 415 volt. So the next ones are, in this case, are normal operation for all the data connection complete supply. In this case, IP equal to VB by ZB. So the 415 by 41.5, you got the I phase equal to 10 ampere. So then you can also calculate the line current. So line current, root 3 phase current. So the root 3 multiplied 10, you got the 17.32 ampere. Then fuse is blown. The fuse will blow. So then this is the fuse blown is a IAIB here, IC equal to 0. Therefore, the current flow to here, in this case, are the IAIB. So what happens is that 41.5 to 45.5 ohms are connected in parallel. And that's also connected in series and parallel with the 41.5 ohms. So IB equal to VB by ZB. We calculate that. So the ZAB divided by VAB by ZAB. So the 41.5, 415 divided by 41.5, you got a 10 ampere. IAB. IAB1 is 10 ampere. IAB2 is going to be a VAB by ZAB2. So that's what we calculate. 415 divided by 41.5 by 41.5, you got this IAB2 is a 5 ampere. Then I equal to IB equal to IAB1 plus IAB2. So that means the 10 plus 5, you got the 15 ampere. Determine the phase voltage and the current for the element of three-phase star connected heater, which has the impedance of the 24 ohm per phase when it is connected to 415 volt 4-hour supply if the fuse in the phase is flow. So in this case, the three-phase are star connection. Supply voltage is line voltage of 415 volt, phase voltage is V by root 3, so that VB equal to 240 volt. In this case, that's star connection 24 ohm. So this is a normal operation. IP equal to VB by ZB. So 240 by 24, you got a 10 ampere. IA equal to IB. So that in this case, IA equal to 10 ampere. IM plus IBA plus IB plus IC equal to 0. So IA equal to 0 ampere. That's what we call it. Then the fuse in the C has blown is IC equal to 0. So in this case, what happens is IC equal to 0. In this case, the IN calculate that IN equal to IL equal to 10 ampere. You got. So DC equal to 0 volt. Fuse blow operation, IB equal to the VB by ZB. So you got this is a VC equal to IC equal to 0. So the what happens is IAB is a VAB is a 415 volt. So current flow to here and all current flow to the 24 and 24. So in this case, I equal to minus IB. Then you got 415 divided by 24 plus 24, you got the 8.65 ampere. Then you got the star voltage, V equal to VB equal to VC equal to V phase. So the VAB equal to root 3 times our VP, so you got calculated. And also the VB equal to root 3 times VB, VC equal to root 3 times VP. So then, so VA equal to VB equal to VC equal to VP. So this is star voltage is a phase capacitor. So in this case, VAB equal to root 3 times VP. Then you got VAB equal to not equal to the root 3 times VP. So this is what a star voltage capacitor. This is delta voltage. VAB equal to VB equal to VAC equal to V phase. So in this case, VAB plus VBC plus VC equal to 0. And delta voltage phase capacitor, that we got. VAB equal to VBC plus VC are not equal to 0. VAB equal to VBC and VC equal to 2 times VAB. So this, if the rotation is correct, this is rotation correct. Voltage reading is 0. Any phase reverse, voltage reading is at 2 V phase. So this is the way we got. The open data connection. So this is supply and there's a load connection here. In this case, 3-phase input equal to 2 single-phase transformer and 3-phase output. So simple and easy to construct the phase and line voltage. In this case, IA equal to ID. Does not have the same power capability. They only got this 57 by 7%. The last way, 3-phase energy and power.
我memory 我录副片呢，中央接那天呢，什么叫跟那的？不了 memory 我录副片呢。你快去我俺那边录啊。
Okay, the next one. Energy and power in three-phase system. At the end of this lesson, students should be able to calculate the true apparent and rated power in a three-phase system, measure the true power in three-phase system. So in this case, we can draw the power triangle. So the horizontal is a real power P, VI cos theta, and the vertical is rated power Q, VI sine theta. And this hypotenuse is the apparent power, S equal to VI. Power factor lambda can be calculated P divided by S. So in this case, real power VI cos theta, reactive power VI sine theta, and apparent power S equal to VI. The power factor lambda of the circuit related to real power to the apparent power. So in this case, cos theta can be calculated P divided by S equal to lambda you got. And the unbalanced of three-phase system. Unbalanced three-phase system, this is a three-phase system, P1, P2, P3, the real power, Q1, Q2, Q3 are reactive power, S1, S2, S3 are the reactive apparent power. So in this case, angle theta 1, angle theta 2, and theta 3 are the power factor angle. So that we add all of them, so that we add the P1, P1, P2, P3, you add, all the Q1, Q2, Q3 you add. Then you can see a total line. So this is the dotted line is a total apparent power. So in this case, real power in the three-phase system can be calculated. Pg equal to Pa plus Pb plus Pc. Similarly, in a balanced three-phase system, this is a balance of all the power triangles are the same. In this case, we can calculate that P total is equal to P1, P2, P3, Q total is Q1, Q2, Q3. Real power three-phase system can be calculated P total equal to Pa plus Pb plus Pc. So the real power in any three-phase system, P total equal to Pa plus Pb plus Pc. In a balanced three-phase system, P total equal to 3 Pp. In this case, 3 multiplied Vp Ib cos theta. In a star connected system, Vp multiplied Ib. This is equal to Im multiplied Vi by 3. Data connected system, Vp multiplied Ib equal to Vl multiplied Im by 3. In this case, P total equal to 3 multiplied Vi Im by 3 in cos theta. So you got the root 3 VAIL cos theta. So this is the way we calculate the total power total. So in this case, power total equal to root 3 times VB IB cos theta or root 3 VLIL cos theta. In this case, VB is a phase voltage, IB is a phase current, VL line voltage, and IL line current. Where to calculate? Determine the true power delivered through the three-phase data connected induction motor, which draws a balanced line current of 20 ampere at the lagging power factor of 0.866 from the 415 50 Hz supply. So the VA equal to 415 volt, IA equal to 20 ampere, lambda equal to 0.866. So PD equal to root 3 VA IL cos theta. Root 3 into 415 minus 20 minus 0.866, you got it. 12 points are 449 watt. So 12 points are 5 kilowatt. The next one is a determine the line current delivered by the 11 kV transformer to a three-phase balance load which uses a 300 kilowatt at a lagging power factor of 0.9. So V equal to 11 kV, PT equal to 300 kilowatt, lambda equal to 0.9. So I equal to PT divided by root 3 PL cos theta, 300K divided by root 3 into 11K into 0.9. So you got 75 ampere. The next one is to determine the true and the reactive power that can be delivered by a three-phase transformer rated as a 50 kVA if the load has a 0.5 lagging power factor. So in this case, our total apparent powers are ST, the 50 kVA, lambda 0.5 lagging. So in this case, we draw the bar here S, B, and Q. So B equal S cos theta. So then 5 lambda. So you got a 50K into 0.5, you got a 25 kilowatt. Q2 equal to square root of S square minus B square, so 50 square minus 25 square, 43.3 kVA. So in this case, our theta equal to cos inverse lambda. So cos inverse 0.5, you got a 60 degree. Theta Q3 equal to SI theta, so 15 multiplied by 0.866, you got a 43.3 kVA. The next one, a three-phase balance loads requires 180 kilowatt of the power when operating at the 0.6 lagging power factor and connected to the 415 volt 50 Hz three-phase supply. Determine the kVA rating and the capacitance of the star connected capacitor band that will improve the power factor to 0.9 lagging. So in this case, firstly, we have to draw the construct the original power trigger. So we draw this power trigger, PD 100 kilowatt. Scales are 1 centimeter, 20 kilo. So in this case, 100 kilowatt we draw. And then also the particle line, we draw the use the rotator and the lambda 1 equal to the 0.86, so that you got the cos inverse of 0.6, you got 51.3, so you draw this line. So this is the original power. So in this case, you measure the particle 1, so this is 240 kVA. So then lambda 2 is 0.9. So in this case, cos inverse 0.9 is 25/84. So you minus 25/84 and you draw the line. And then you measure, so Q2 equal to 88 kVA. So this is the kVA rating. So that's the difference between the Q1 and Q2 is the red one. So Q is equal to found 240 minus 87, you got a 153 kVA. So the three-phase balance load. So in this case, we have to calculate capacitance of the capacitor band. So it is QC 154.53 kVA. So the QB equal to QC by root 3 because of the three phase, right? Every phase. So this is the phase of reactive power can be calculated QC by 3. It is 153/3. You got the 31 kVA. And then you have to calculate the HB. PB square divided by QB. So you got PB can be calculated PB by root 3. So you got the 240 square divided by the 51000. You got the HB equal to 1/130. HB equal to 1 divided by 2 by FC. You substitute. C equal to 1 divided by 2 by FHB. So the 1 divided by 2 by into 15 1/130. You got the 2/82 millifarads. So this is the way we calculate it. So the power factor in the three-phase system. In this case, 1 meter we both connected. So N and L1, V1, V2 here. This is the what? W2 and W3. So the P total is equal to PA plus PB plus PC. So the advantage is it can use, this is for the 3 1 meter and 4 wire method. It can be used for on the balance or unbalanced load. Total power easily monitor. So reasonable accurate. So disadvantage is the 3 1 meter required. It requires a neutral or scarce system. So in this case, only 1 meter methods move from phase to get each reading. So in this case, 1 meter, you can move from phase to phase and you can read. So the P total is PA plus PB plus PC. And power measure in three-phase system, so this is a 1 meter connected here. And this is the only 1 meter required. Simple and cheap, can be used on a balanced or unbalanced load. Disadvantage is not very accurate in unbalanced load. So this is for the connected. So this is for artificial star wire. The 3 1 meter method is we connect as artificial star wire. Can be used for the balance or unbalanced load. Total power easy monitor, reasonably accurate. Disadvantages are require the 3 identical 1 meter. Another thing is 1 meter and a 3-phase wire method. So this is the connection. So this is for the connected to the artificial star wire and you connect this 1 meter. So the only 1 meter can be used simple and cheap. Can be used on the balance or unbalanced load. Disadvantage are the must be construct artificial star wire. Not accurate on variant unbalanced load. Need to reconnect each phase for the unbalanced load. And there are 2 1 meter method. So we connect the 2 meter like this, P2 will be P1 plus P2. And advantage can be used on the balance or unbalanced load to the power easily monitor. Only 2 meter required. Disadvantage can be used with the 3 wire system only, not accurate for the load with the low power factor. And so this is a 2 meter procedure. So P2 is equal to P1 plus P2 for balance load. Locate the W2 in the phase immediately following W1 in the phase sequence. So theta equal to root 3 times W2 minus W1 divided by W2 plus W1. So this is 2 element 1 meter equal can be utilized. This is for the G102. Then we also go to the G101.